Alrighty. Very excited to be here. I think I hopefully have an interesting talk for you today. It's a bit of a lofty title, but everything I show is really applicable in many different contexts. What I show you is game-based, but that's really just because it's more fun to watch. But a lot of these technologies that I'm going to show you can really be applied to enterprise solutions. And you'll understand that I actually come from an enterprise background. I'm not a game guy. Yeah? So I was head of machine learning and AI at Uber before coming to Unity. I was leading the work on the Michelangelo platform, which was a machine learning platform. It is a machine learning platform used across Uber, both for the Uber app, other Uber businesses such as Uber Eats, and the self-driving car projects. And before that, I was at Amazon. I ran Elastic Machine Learning, which was the internal cloud service for machine learning at Amazon, used by up towards 100 teams at Amazon. I also launched the first machine learning service on AWS, Amazon Machine Learning, when I was there. Before that, Microsoft, before that, IBM. I've done this stuff for a long, long time. A quick words about Unity so that you sort of get the context here, because why would I go from Amazon and Uber and Microsoft to a game company? Well, it's not just about any game company, it's really a game platform company, and it's more than gaming, it's really a 3D platform for not only games, but AR, VR, film, and automotive. I will show you some examples. We have about 60% of the world market for game development, so we are like a platform for game development. We have our bits are installed on about 3 billion devices, all kinds of mobile phones, consoles, PC, Macs, other kinds of devices. And we have about 1.5 billion monthly active players playing a game developed on the Unity platform. So it's pretty massive and fast growing. 2,000 employees headquartered in San Francisco. We have about 250 people next door in Lincoln Square, where I have a big part of my machine learning team. We talk in an enterprise context, and this morning here we talk a lot about machine learning and data science and all this stuff. You know, I've been in that space for quite some time. I spent 8 years developing virtual voice assistants. Surprisingly enough, Siri and Alexa today is implemented pretty much the same way we did in 1997. Yeah? Linguists, creative writers, and a bunch of software engineers, and then we script it all out. Yeah? Not much of AI there. Okay? And maybe a machine learning piece here and there to do text-to-speech or to do speech recognition, but AI, nope. Amazon Netflix recommendations. You know, Netflix recommendations today is a very simple algorithm. It says, you know, recommend if produced by Netflix, otherwise put it somewhere else. Yeah. You know, roughly like that. Yeah. It's not like the old days with the Netflix prize and the competition and advanced recommendations. Now it's really a different game. Yeah. Amazon recommendations, a lot of really bright people writing some bright algorithms that do some clever stuff, but again, not really AI. Yeah? Fraud detection services, I can go on. Equity trading, there's a lot of deep learning in equity trading nowadays, but again, it's smart people using smart algorithms to solve problems. Yeah. The Facebook feed, I think we should skip that one when we talk about intelligence. And the only really success that I can see of AI right now is the titles on LinkedIn. There's a lot of them, yeah. So what is intelligence really? This is the dictionary thing, and it's sort of a little abstract to me, so I can't really use that either. It's something about acquiring and applying knowledge and skills. So I want to take sort of a step back, a step up, or whatever you want to call it, and basically ask the question, what's the only real intelligence that we know? Well, it is the intelligence in biological systems, yeah. Any other kind of intelligence, I don't really know what that is, yeah. that becomes awfully abstract, but nature created, sensors and computation for us, and why did it do that? Yeah. So why did it create intelligence in humans and animals? Yeah. Well, it's really 5 principles. Number 1 principle is caused by physics. It's the entropy. Yeah. We need energy to maintain structure. The molecules and structures of life, entropy wants to kill that and make it sort of some gray, uninteresting stuff. Yeah. So we need energy. We also have to watch out when we try to get energy that we don't become energy ourselves. Yeah. This is a core part of nature. Yeah. Since some of us has a tendency to die, we need to produce more of us all the time. Yeah. And we need to be aware of physics when we climb the tree to fetch an apple. Don't fall down, break your neck. Don't fall over the cliff, etc. Yeah. So physics plays a role here. And the last principle is agency. That is that we try to shape nature. Even if we're a little mouse, we try to create, or bird, we try to create a nest. Yeah? So we do something with our environment to increase our survival rate. Yeah? So those 5 principles really led to creation of this. Yeah? Neural systems in nature. Yeah? Nature created infrastructure to get going. Yeah? Those 5 principles really forced nature to invent something. Yeah? So it invented chemical mechanisms. It invented a variety of cellular structures. It all started out with being RNA in a big soup, and then it sort of figured out to do cell membranes and nucleus of cellular structures, etc., etc., etc. Yeah. So more and more structure, multicellular organisms where there's communication. Muscles, I can think and control my muscle, all that kind of stuff, eyes, hearing, etc., etc. Yeah. So all this infrastructure was created by nature to achieve intelligence. Yeah. And then look at the game engine. Yeah. Now I want you to seriously sort of do the transition here and say, a gaming engine is this 3D environment with a physics engine. And it's enclosed, yeah? And what do you face in game engines? You face actually some of the same things that I just talked about, yeah? Collecting something while avoiding getting, meeting the Pac-Man enemy or whatever, yeah? Physics, don't fall down, don't get hit, all the same kind of stuff, yeah? So if you think about it, the principles in nature and evolution, and then you take a game engine, you actually have your private, biodome for exploring AI. Yeah? So rather than trying to break new ground in machine learning by do book recommendations for Amazon, you can really start taking a page out of the playbook of nature, shove it into a game engine, and now see if you can actually develop some of that kind of intelligence that we as humans and a bunch of animals have developed over many, many years. Yeah? So it's not entirely a new idea. It has been around for a while. We have seen a number of attempts to create bots that use pixel learning, play arcade games, stuff like that, where they see things, the computer interprets what is with the pixels and will do some action based on that. We have seen physical environments where humanoids learn to walk through reinforcement learning, and probably the oldest discipline in this space is having computers playing board games. Yeah, starting in 1949 with Claude Shannon building the first chess game. Yeah, up to AlphaZero that learns to play chess, shogi, go all by itself. Yeah, so that's the cognitive side. Yeah, not a lot of physics there, not a lot of visuals. That's cognitive. Yeah, so we have seen these separate attempts to explore aspects of AI that way. Now take the Unity ecosystem, about 1,000 new games launched every day, yeah? And it goes from mobile devices to console games, yeah? AR, VR, yeah? So you have, in this game environment, you have all of what I just talked about, yeah? You have the high fidelity visuals, you have physics, control, and you have cognitive challenges and puzzles, and you have it all in one package. Yeah? So that's why I came to Unity, because I look around and say, where can I really push the limits on AI without, driving into people with my self-driving car? Yeah? Where can I do it safely, and where can I push it, and where can I push it at scale? Yeah? So at Unity, we are working closely with DeepMind in London. DeepMind is actually using Unity. They have rolled it out for all their researchers, and they run it in the Google Cloud structure or infrastructure to basically use game-like environments to push the limits of AI. Okay, so this is more than playing Go. Yeah, we're getting into something else here. Yeah, and what I want to talk a bit about today is what we call learning, nature's learning method, which is essentially a feedback loop of observing, taking action, and either take the punishment or the reward from that action. Yeah, and funny enough, this is also like a core algorithm at a company like Amazon. Yeah, yeah. Every page on Amazon has this feedback loop in it. Yeah? Every page is a unique page that only you see. There's stuff there. It's based a bit on what the company knows about you and some random exploration. Yeah? And you click on something, they learn something, you don't click on it. There's actually a little snippet of JavaScript in an Amazon web page that makes sure that they know what you see and know what is below the screen, yeah? So if you don't scroll down, you don't see it, because they want to know if you see it and don't click on it, or if you see it and click on it, yeah? That's all important knowledge to move from exploration to exploitation, yeah? Yeah. So known algorithms here are, for instance, like the multi-arm bandit algorithm, which is one of the most popular algorithms at Amazon, yeah? So that's the one that spins its wheel behind every page you see, yeah? I want to take that a step further, and at Unity we ask ourselves if we, from Tabula Rasa, from a clean slate with a generic reinforcement learning algorithm, can have a chicken learn to cross the road, just based on pixel learning, pixel observation, no hard integration with the game. We only tell it has 4 actions. We know they're left, right, forward, backward. Actually, the system doesn't really know. There's just 4 actions it can take. And there's reward signal. You get hit by a car, not a good idea. That's a negative. And you pick up a gift package, and it's a positive. Yeah. So look at this little video. You'll notice that the chicken starting out here actually knows nothing. It's complete random movement. Yeah, it moves sort of more backwards than forwards. But in a moment, it will pick up the gift package there on the right side there, and then it got killed. Yeah. So 2 pieces of information within whatever 10 seconds. Yeah. Do that for half an hour, and it gets pretty good at it. Yeah, it will pick up gift packages. It will avoid the cars, and it's a completely generic algorithm. Yeah. This is just a trivial reinforcement learning algorithm, and it learns, have a convolutional net in front, so it learns to interpret the pixels as well. That's just a byproduct. Now look after 6 hours of trial and error. It looks something like this. Yeah, yeah. The chicken became superhuman. Yeah. Yeah. And notice that at some point, I think in a moment here, it stops actually for a moment. It does a little, it will continue forever, yeah? Cars and gift packages are random, yeah? So it's never seen this before, yeah? Yet it will not get killed by a car. It will not. So that gives us an idea that, this trial and error that nature is doing is actually pretty powerful, yeah? And it works at scale. And don't dismiss scale. A lot of people say, oh, I want to use, I don't want to compute that much. Look at nature. It just computes a lot all the time, yeah? Nature's not really trying to optimize on that account. Yeah. By the way, I never told it to actually cross the street, yeah, or road. Yeah, it's moving forward. Why is it moving forward? Because I didn't ask it to do that. I just said pick packages and don't get killed. Yeah. So why is it moving forward?
Because there were packages there.
There are more packages in the future, yeah, than behind you because you did pick them up. We call that emergent behavior. Look for that in reinforcement learning all the time. You sort of ask, you give it some rewards, and you get some effect out of that. In this case, an obvious effect. It crosses the street, yeah. But in some cases, it may be an unwanted outcome that you didn't predict. Today, we are roughly, I would say, the #1 choice of platform for this kind of reinforcement learning work, yeah. We have a release on GitHub. Everything is open source. ML Agents is basically a framework that hooks into the Unity engine. So if you create an environment or you take someone else's environment, you can do reinforcement learning on it without going into all the nitty-gritty details of integration. Yeah. You create environments in Unity. It's like a game development, so you have edges, you create environments, you can train your agents using ML agents, coupling it up through Python to your favorite machine learning system. We are using TensorFlow a lot, and then in some cases you actually may want to embed those machine learning models back into the game and put it on the phone. Yeah. I'll show you some scenarios, some learning scenarios here. Here's one of a quadruped. This is an example where the rewards function is really very simple. It just says move forward, and then the system will try and figure out how to move the different joints and how to move them in a proper pattern to move forward. Yeah. So it's basically a small example of, I'm going to develop a robot. Am I going to sit down and code it in C, or am I going to use reinforcement learning in a simulator to learn to walk, yeah. So that's one observation here, yeah. So this has actually engineering implications, yeah. The other interesting thing is, of course, that nature, if you sort of look at this, nature came up with a similar way of walking, yeah. We're not cheating here. We start with Tabula Rasa, yeah. So it will for 10 minutes probably just wiggle around and not really figure out how to move until it hits, hits the right pattern of movements, yeah. I want to show you another one here. The rewards function is sort of -1 if the ball hits the floor, yeah? So keep the ball going, yeah? Again, from a clean slate, you see behavior that is sort of kind of interesting. You start thinking about the physics that is learned by this neural net. Yeah, it's something about predicting the future placement of the ball, because you can't move the bat unrealistically fast. It can only move at a certain velocity. Yeah? So the neural net needs to do some hand-eye coordination here, if you think about it. Yeah? Which is another interesting thing, that you can have very complicated physics, very complicated functions learned and implemented in a neural net, and you don't even know it. Yeah? So a lot of these problems I show you, smart engineers will say, well, I can solve that too. Yeah, you can. If you're educated and you know your physics, you can do it. Yeah? But of course, as things get more and more complex, it becomes harder and harder to really understand all the physical aspects of doing something. Yeah? So last summer we had World Cup in soccer. We got inspired. Can we train a small soccer team, yeah? 2 players. Want to have an offensive player, striker. The striker gets rewarded by scoring goals, yeah? So that's it, yeah? You score, you get a point, yeah? You need a defensive player to have a team. You have an offensive striker, you have defensive player. Defensive player get a negative reward if a goal is scored upon them, yeah? So that's very simple. How do we train these 2 systems? There's 2 machine learning systems, yeah, an offensive one, a defensive one. Well, just put them up against each other, yeah. Initially, they would be pretty bad. One guy can't hit the goal and the other one can't defend it. But after a while, they will converge, yeah. and make each other better and better until they converge, and you have as good a defensive player as you can have, and as good an offensive player as you can have, yeah? And then what do? Well, we copy those two models and create two teams, yeah? Two teams, a striker in each and a defensive player in each. Put them together and let them play against each other. It looks like this, yeah? So what you see here is, funny enough, the defensive player, which I really only defined as minus, you get a negative reward if you're being scored upon, clearly became a goalie. Yeah? They don't move very far from the goal. Apparently that's not a good idea. If you're a defensive player, protect your goal. The little white thing is an eye, so you see where they're looking. They're looking upfield, yeah? Yeah? The other player here, the striker, look at them, they're running sideways because they're looking sideways. Why are they looking sideways? That sounds weird, doesn't it? Well, if you're looking sideways and you're up along the line, you see the entire field. Yeah? You have the entire field in front of you. Yeah? So you can see what's going on. What's striking here to me, I have had little kids who played soccer when they were like 6 years old or whatever, and there would be these things going on, like always attack along the line, don't run in the middle of the field, you don't have a chance in there, yeah, up along the line. These guys figure out to learn, you know, the computer learns the same thing, yeah, up along the line. Yeah. Again, examples of what we call emergent behavior, yeah. The goalie, not my invention, it learned it, yeah. The striker up along the line, not my invention, it learned it by trial and error, yeah. More interesting stuff, like if you want to solve really hard problems, and if you, for instance, want to get over a wall. This is actually an old example that now became very, very kind of timely. So if you want to scale a wall, can a computer learn that? Yeah? Can the agent learn that? Yeah? And if the wall is really high, it gets complicated, it can't jump by itself, so it needs a stepping stone to get over the wall. Yeah? So it's a pretty complex problem for computers to randomly learn that if the wall is this high, I need to push a cube to the wall, step on the cube to scale the wall. Yeah? If the wall is lower, forget about the cube, just jump over the wall. Yeah? So what we found is that you can benefit from starting easy. Don't throw the computer into the deep water here. Start easy, like with a tiny, tiny wall. When it gets good at jumping a tiny wall, make the wall higher. So basically, make the task incrementally harder. Yeah? So don't do a simple machine learning training problem. You know, I have this problem here, train on it, done. Yeah? No, make it easy and then incrementally harder. And it looks like this. The outcome looks like this. You use the orange, and in this case, it can just jump. Yeah. So it sort of gets pretty advanced. It's using a tool to scale the wall when it can't do it on its own. Yeah. What's interesting here is that if you just do a single long training loop on the hard problem, just give it the hard problem. Yeah. That's the orange one. It takes a long time to learn, and the model gets never gets really good. Yeah. The blue one is a curriculum learning. It's like start easy, and then every time you graduate by having good performance, we raise the wall a bit. So raise. Yeah. And it learns faster, and the model you get, the neural model you get out of this, is better performing than the other one. Isn't this why we go to school in first grade, second grade, third? It's something about how neural nets, they get formed. Yeah. That if you just jump into a very hard problem and try to learn to deal with it from the get-go, you never get the right structures in place for it. So again, a small example of how neural nets really emulate what we already know from nature. Yeah? Other examples are a simple reinforcement learning algorithm. If you can't see the entire world, the entire environment all the time, it doesn't really have memory capabilities. So we threw LSTM in there, long short-term memory capability in there, and say, agent comes in, agent C, this orange block. If it's orange, it needs to do the orange exit. If it's red, it needs to take the red exit. Yeah. The moment that the agent passes by that cube, it needs to retain the memory of that color to pick the right exit, yeah. So this is a small example of working memory, yeah. And the way it looks is here, it learns quickly to pick the right exit, yeah. Interesting enough, we actually never tells it it's the color that matters. We basically just give it a +1 or -1. But we never tell it it's the color, dude, yeah. We never say that. So it could have been the size, the shape, the position, could be many things. Interesting here is that it learns, this is an example that's very important, yeah? It learns to memorize, or it learns to remember in the working memory, it learns to store what matters without us telling it. So basically, again, by trial and error, it figures out, if I store the color of that cube in my recursive neural net, when I get towards the exit, I know which one to take. Yeah. Again, an example where it's not an engineer saying, this is how to solve the task. Yeah. There are other examples, humanoids. Again, it's kind of interesting that the computer kind of gets to pretty close to how we run. Not all the way there, yeah? But that was not the attempt here. It was just with some rough physics saying, did nature teach us the right way to go and run? Yeah, it did, apparently. So let me jump into something new. This is just, you know, stuff that's within the last year. And this is where we look at a combination of extrinsic and intrinsic rewards. And this is where reinforcement learning sort of takes us not only maybe a leap forward, it gets really interesting, yeah? Extrinsic rewards, we know them very well. We know them from gaming. It's capture the flag, capture points, gold coins, Pokemons, whatever. Yeah? Is this thing that's specific to the environment? Yeah, we compare it to getting rich. Yeah, it's having 2, 3, 4 cars in front of your house and a big number of the bank account, stuff like that. Yeah, that's extrinsic. We see it over and over in reinforcement learning, yeah? Gather more of this, gather more gift packages, yeah? While you're not getting killed. Gift packages, yeah. There are intrinsic rewards too. Nature equipped us and many, many animals with things like curiosity, impatience and patience, happiness, love, empathy. All these things, we equip with those traits because they matter for survival. They give us an advantage. Yeah? When I ski up at Crystal Mountain, and you take the first chairlift up, goes between the trees, and you can always see the animal tracks in the snow. Yeah? The squirrels are out in the snow, deep snow, yeah, looking for food. Yeah? Do they run around in the middle of the big white stuff? Or do they sort of run around trees and bushes? Yeah. You can see that they are not random in their exploration. Yeah. They're not random. They apply some sort of curiosity. They see something and they say, huh, maybe there's something over there. Yeah. Yeah. So curiosity is a very good example that I'm going to get a little deeper into. Yeah. I showed you the chicken, yeah, the exploration on going to exploitation. The exploration is typically random, yeah, and works in many ways that way. But there are cases where it doesn't work. So when you go to sparse reward spaces, I call them Agatha Christie event chains. I don't know if anyone here ever read Agatha Christie, but it's sort of in the first page of the plot. It's pretty unrealistic, and then you go to page 2 and it adds even more, I mean, like what I would call ridiculous, improbable scenarios to it. Yeah, it is like this needs to happen and it's unlikely to happen, but it happens, and then on the next page something that's even more unlikely to happen is being bolted upon that plot. Yeah, and then it ends up being like it's never going to happen. Yeah, well, we created one of those scenarios for our agent. Yeah. We let the agent enter a house, lots of rooms in the house. In one of those rooms, randomly a push button is going to appear. It doesn't know anything, yeah? But we know that you need to push the push button, and then a rock pyramid or stone pyramid will appear in another room. On top of that pyramid is a gold bar. You need to knock over the pyramid. Gold bar needs to fall down, and then you can grab it. And that's your extrinsic reward. Collect gold bars, yeah? If we just let it use randomness, it will likely, even with a lot of AWS or GCP or Azure cloud services, never really figure it out. It's just too unlikely chain of events, yeah? And you have to think about these sparse reward spaces. They happen all the time, yeah? Take Amazon, yeah? 300 something secret number of million customers, yeah? 300 something, let's just say that, yeah? Any guesses how many products in the catalog? 1 billion plus catalogs, yeah? So they have 1 billion SKUs, 300 something million customers, and then they have third-party sellers, yeah? Not just Amazon.com, but all the people who sell on Amazon, yeah? So that's the third dimension, millions, yeah? Think about that cube, that matrix, yeah? Billion times 300 million times many millions. And then you shop at Amazon, you're one of those, and you think you buy a lot of products, yeah? But in that cube, you're nothing, yeah? All Amazon sales in that cube is sparse, yeah? So a lot of common business problems are sparse, yeah? And that's why things like intrinsic rewards are so powerful, because they give us a strategy to navigate these sparse spaces, yeah? So we formulated curiosity mathematically. It's actually very simple. If you look at the arrow there, is the minus log is the key here. Yeah? What we always do in machine learning is trying to be as right as possible, yeah? We want to maximize the probabilities, yeah? Curiosity is learning the opposite. Curiosity is actually learning to look around and identify items where my prediction will completely fail. Yeah? So the squirrel looks in the snow, it's nothing interesting, but it sees a tree and it says, I don't know what's behind the tree, so let me go and check it out. Yeah? Yeah? That's curiosity. That's also how science works. Yeah? We look around, see all the stuff we know, we don't care about that. There's something we don't understand, something we don't know, we'll take a closer look at that. Yeah? So that's that. This is a fairly new invention. In machine learning has been right in front of us all the time. Yeah? Here we have the agent in the house. Random exploration. Getting nowhere, learning nothing, figuring nothing out. Yeah? This is basically how Amazon is trying to figure out if you're interested in something. Just randomly picking books and see if there's some interest. Yeah? Yeah? In the next example, we added curiosity to the agent, but no external rewards. So it does not have a purpose in life. It's not trying to get rich. It's just trying to be curious. And watch it in that context, yeah? It's trying to be curious. It sees something, it explores it, yeah? So it figures out that when it hit those rock piles there, the pyramids, something happens to them, yeah? So it's curious. It's trying to figure out what's going on here, yeah? But it does not have a real, it's not trying to achieve something with it, yeah? Curiosity works in some cases actually really, really well. Anyone try to play Breakout? The game where you shoot down bricks. It's a very old Game Boy thing, many years old, yeah? You shoot down bricks with your pad, and when all the bricks are down, new bricks appear and you shoot those down, yeah? You can play, an agent can play that game only based on curiosity and become superhuman without ever getting the score back. No extrinsic reward, purely intrinsic. Just, why? Why does it learn to play the game? Because if it fulfills one game level, there's a new game level with new stuff. So it will basically learn to satisfy curiosity. It will try to get to that next unknown game level. So it will just keep playing. without extrinsic rewards. Yeah. Now, let me get back to this one, and let's give the agent both curiosity and a desire to collect these gold bars. And it looks like this. It gets very, very directed now. It looks for that push button, hits it, looks for the other pyramid with the gold bar, there it is, knocks it down, and pick up the gold bar. Come on. Yeah, there we go. Yeah. It figures out that ridiculous, improbable event chain and has a solution to it. Yeah. Okay, can you imagine, again, I'm going to do product recommendations, yeah, and I'm going to learn something like, if I get you to buy a book on barbecues, I know you're going to come back and buy a grill next month, and then you're going to quickly buy some tools for it, and then at the end of the month, you're going to sign up for Amazon Fresh and get steaks every day. Yeah, I'm going to learn that sequence, yeah, the sequence that you don't even learn yourself. So I want to show you another example, a virtual robot dog. So game characters are typically, you know, you roll in the whole Disney animator thing and software engineers and they implement everything. What we did here is that we basically said, here's a dog, it can move, and we're going to train it. We're going to put it in camp, and it's going to have to learn to walk. And, you know, they're not very good at it, obviously, yeah. The stick is right there, that's the extrinsic reward, yeah. Bring back the stick. And it's trying to figure out how to move 4 legs in some clever pattern that moves it in the right direction. Yeah. Yeah. So you train and train and train and train and train, and it looks like this when you're done. I throw the stick with the mouse. You can see the mouse there. I pick up the stick and I throw it. Whoop. And there's no animation programmed here. It's all learned. Yeah, the whole behavior is learned. Bring back the stick. That's the reward. Yeah. Now look what happens here when I throw the stick. Whoops. Yeah. So you have to think that, I mean, like, this is actually, think about it. It's really powerful. I can throw that stick anywhere, anyhow, and it will pick up the stick. Yeah, because it trained 1,000,000 times to pick up sticks. And it learns to turn around. Think about all the complex movements here. Yeah. I can show more examples of this. You can also actually, we heard about TensorFlow Lite, yeah? You can take your TensorFlow model here and put it on the phone and play the game there, yeah? Here's another example. The dog is chasing the bone, and we have 10 dogs. What's interesting here is that normally when you do this in gaming and movies, you implement flock behavior, yeah? In this case here, it's really individual behavior, but each dog take up space, yeah? So it's really physically driven. Notice that some of the dogs, they get pushed out and fall over and stuff like that. It's not an artist, it's not a studio boss who designed this game, yeah, and decided this behavior. It's nature, yeah? Oh, sorry, too fast here. Everything I showed you is available on GitHub. Yeah? So you can download all this code, you can download the framework, you can download Unity if you don't have it, and you can like play with it, you can modify it, you can tweak it. Yeah, it's all on GitHub. This is the address. We have thousands and thousands of people subtly doing advanced reinforcement learning and getting it at the same time, compared to sort of boring data science. Sorry. But I hope you understand that actually there's a company in Europe, they emailed me and said they're implementing this curiosity for their product recommendation system. It's a company that has mobile phones and mobile phone plans, an awful lot of them, and it's very complicated, you know, what plan to pick to what phone for what kind of people. And they think actually the curiosity will help them recommend better plans. Everything I showed you today, we are cheating. Yeah? I have people on my team who are not computer scientists, but actually come out of neuroscience and biology. We're cheating because we are stealing left and right from nature. Attention, I love that one. Our brains are really good at paying attention to stuff, and then we don't see a lot of stuff around us. If you have an Uber self-driving vehicle, it has 600 sensors, a 3 kilowatt server in the trunk processing this, and it's spending as much energy looking backwards as forwards, though I think forward is more important than backwards, yeah? So things like that. Attention is a good thing to implement. One-shot learning, you know, when you experience something really bad, you tend to remember it and don't do it again, yeah? Working memory, I showed you that one. Continuous learning, which is a funny one. Computers. If your neural net is very quick at learning, it's also really quick at forgetting what it learned if you train it to do something else, yeah? Well, it happens to children too, yeah? I had 2 children, we lived 6 years in Japan, moved to the US, they were fluent in Japanese. 6 months later, they couldn't count to 3, but now they spoke English, which is like, okay, that was fast, yeah? Later in life, that elasticity goes down. It's hard to learn new stuff, but then also the stuff we already learned kind of gets stuck, yeah? So machine learning has exactly the same problem, yeah? If you're really fast at learning new stuff, you overwrite the old stuff, yeah? So imagination, dreaming, that's just simulation, yeah? Intrinsic values, I talked about that, yeah? Hierarchical learning is another one that's really cool because we have a lot of that, yeah? So you see something, you decide to do something, that's multiple models, yeah? And then at the very low end of it, your legs move in a certain pattern to bring you in that direction, yeah? Super powerful in machine learning. If you use hierarchical modeling, you have eyes that look, convolutional nets, you have a planning layer, and then you have the layer that actually moves the dog's forelegs to make it do the right things to achieve its goal. Yeah? You don't try to have one big model solving everything. Yeah? At last slide. I want to leave you with one thought here, which is pointing a little out to the future. Yeah? Humanity is not new. Homo sapiens, 200,000–300,000 years old, started migrating out of Africa 100,000 years ago, didn't go that well, so waited another 30,000 years and then started migrating 70,000 years ago, came into Australia by boat 45,000 years ago. Around between 30 to 70,000 years ago, there was like a cognitive revolution. Something happened. The figure out on the right side here is 32,000 years old. It's called the lion person. And 32,000 years ago, we started doing stuff like language, like collaboration, like art. Start having fiction. The figure out on the right is actually a human with a lion's face. So it's like, that's fictional. Those things don't exist, yeah? So something happened at that time that sort of changed humanity, yeah? However, keep in mind that since those 30, 40, 50,000 years ago, the DNA has not changed much, yeah? So the processing power of a human being today, of this one, yeah, is the exact same as it was 50,000 years ago, yeah? Yet, 50,000 years ago, we were really sort of digging around in the forest, yeah? And picking berries and try to kill game, yeah? So, we are today where we are with all our moon landings and nuclear power plants, etc., yeah? But the individual processing power of each node in the network has remained the same, yeah? So what it should tell you is that sometime very soon we need to explore machine learning systems that do work together and find ways to work together that we don't code, yeah? So everything I showed you today are individual training examples, yeah? But what if I were to train a group of dogs to work together? And I'm not telling them how to work together. I'm not telling them what language to use. They will learn that as well. And what if you do those simulations at scale in some cloud service, yeah? There are people today who actually are running hundreds of thousands of instances of Unity, creating training data for that kind of scenarios, yeah? So don't dismiss the capabilities of machine learning and AI today at the individual level. Think about what happens when you start getting those not very capable processors to work together in very large networks and work together in ways we don't really know. Yeah. I want to leave you with that thought, which I hope will inspire you. And you're welcome to link up on LinkedIn or follow me on Twitter, whatever. We have a big announcement on Monday. We're going to come out with a video game. We spent a year developing a video game just to be played by computers, not people. But check that out Monday. Thank you.